The data table provides information about the buck-boost transformer's input and output voltages, power ratings, and wiring configurations under various conditions. Input voltage refers to the voltage supplied to the transformer from the alternating current power source. Output voltage refers to the voltage that the transformer will provide to the load. Output wattage indicates the maximum power output that the transformer can deliver. Turns ratio refers to the ratio of the number of turns on the primary winding to the number of turns on the secondary winding. To determine which wiring diagram to use, you need to consider the following. Firstly, input voltage. Since the system is 120/208 volts, a diagram that supports 120 volts input is needed. Secondly, output voltage 12 volts alternating current is required for the track lights. Thirdly, turns ratio. As this information is not given, examine the diagrams and select the one that matches the input and output voltages. Diagram is for a buck configuration, which reduces the output voltage and is not suitable for this application. Diagram B is a boost configuration, which increases the output voltage. It is suitable for a 120 volts input and 12 volts alternating current output requirements. Diagram C is for an isolation configuration, which maintains the same output voltage as the input. It is not suitable for this purpose. Based on the above analysis, use diagram B, boost configuration, to connect the 12 volts alternating current track lights to the 120/208 volts power source using the buck-boost transformer. Always consult the specific manufacturer's instructions for detailed wiring and safety precautions. When working with electrical systems, it's crucial to understand the terminology and concepts involved. A transformer is a device that transfers electrical energy from one circuit to another through electromagnetic induction. Buck-boost transformers are a specific type of transformer that can either step up or step down the voltage depending on the wiring configuration. The primary winding is the input side of the transformer, while the secondary winding is the output side. The turns ratio is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding, and it determines the voltage transformation. When selecting a transformer, you need to consider several factors, including the input voltage, output voltage, power rating, and wiring configuration. The input voltage should match the voltage of the power source, while the output voltage should match the voltage requirements of the load. The power rating should be greater than or equal to the power requirements of the load. The wiring configuration should be chosen based on whether you need to step up or step down the voltage. In this case, a boost configuration is needed to step up the voltage from 120 volts to 12 volts alternating current. When working with electrical systems, it's important to follow all safety precautions. Always disconnect the power before working on any electrical equipment. Use appropriate personal protective equipment, such as gloves and safety glasses. Follow the manufacturer's instructions for wiring and installation. If you are not comfortable working with electrical systems, consult a qualified electrician. In the provided scenario, there is a 120/208 volt system supplying line to neutral circuits for the track lights. The track lights require 12 volts alternating current, so a buck-boost transformer is used to step down the voltage. The transformer has a model number of 750 SV43F, and it is likely a 750 watts transformer. The data table provides information about the transformer's input and output voltages, power ratings, and wiring configurations. To determine which wiring diagram to use, consider the input voltage, output voltage, and turns ratio. Since the system is 120/208 volts, you need a diagram that supports 120 volts input. You require 12 volts alternating current for the track lights. Examine the diagrams and select the one that matches the input and output voltages. Diagram A is for a buck configuration, which reduces the output voltage and is not suitable for this application. Diagram B is a boost configuration, which increases the output voltage. It is suitable for a 120 volts input and 12 volts alternating current output requirements. Diagram C is for an isolation configuration, which maintains the same output voltage as the input. It is not suitable for this purpose. Therefore, use diagram B, boost configuration, to connect your 12 volts alternating current track lights to the 120/208 volts power source using the buck boost transformer. Always consult the specific manufacturer's instructions for detailed wiring and safety precautions. Understanding the different wiring configurations is essential for proper transformer operation. The buck configuration reduces the voltage, while the boost configuration increases the voltage. The isolation configuration maintains the same voltage. Choice of configuration depends on the specific application and the voltage requirements of the load. When connecting the transformer, it's important to follow the wiring diagram carefully. Ensure that the input and output voltages are correctly matched. Use appropriate wire sizes and connectors. Properly ground the transformer to prevent electrical shock. After connecting the transformer, test the output voltage to ensure that it is correct. If the output voltage is not correct, double-check the wiring and the transformer configuration. If you are still having problems, consult a qualified electrician. Transformers are essential components in many electrical systems. Understanding how they work and how to connect them is crucial for ensuring safe and reliable operation. By following the guidelines and safety precautions outlined here, you can successfully wire 12 volts track lights using a buck boost transformer. Always remember to prioritize safety and consult with qualified professionals when needed. The information provided is intended as a general guide and should not be considered a substitute for professional advice. The NEC, or National Electrical Code, provides comprehensive standards for electrical installations. It is essential to adhere to the NEC guidelines to ensure safety and compliance. The NEC covers various aspects of electrical systems, including wiring methods, overcurrent protection, grounding, and equipment installation. When working with electrical systems, it's important to be familiar with the relevant NEC articles and sections. Some examples of NEC articles that may be relevant to this scenario include Article 250, Grounding and Bonding, Article 300, Wiring Methods, Article 310, Conductors for General Wiring, Article 450, Transformers, and Article 725, Class 1, Class 2, and Class 3 Remote Control, Signaling, and Power Limited Circuits. The NEC is updated regularly, so it's important to use the latest edition. Local jurisdictions may also have their own electrical codes and regulations which should be followed in addition to the NEC. Consulting with a qualified electrician or electrical inspector can help ensure that the installation complies with all applicable codes and regulations. Proper grounding is essential for electrical safety. Grounding provides a path for fault current to flow back to the source, which helps to trip the overcurrent protection device and prevent electrical shock. The grounding system should be properly installed and maintained to ensure its effectiveness. The NEC specifies the requirements for grounding electrode systems, grounding conductors, and bonding conductors. Bonding is the connection of metal parts to create an electrically conductive path. Bonding helps to equalize the voltage potential between different metal parts, which reduces the risk of electrical shock. The NEC specifies the requirements for bonding metal enclosures, equipment, and other metal parts. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overcurrent protection devices should be properly sized and installed to provide adequate protection. The NEC specifies the requirements for overcurrent protection devices, including their ampacity, interrupting rating, and location. Wiring methods refer to the types of wiring and installation techniques used in electrical systems. The NEC specifies the requirements for various wiring methods, including conduit, cable, and wireways. The choice of wiring method depends on the application, the environment, and the applicable codes and regulations. Conductors are the wires that carry electrical current. The NEC specifies the requirements for conductors, including their ampacity, insulation, and size. The ampacity of a conductor is its current carrying capacity. The insulation of a conductor protects it from damage and prevents electrical shock. The size of a conductor is determined by its ampacity and the length of the circuit. Transformers are used to change the voltage of electrical power. The NEC specifies the requirements for transformers, including their installation protection and grounding. Transformers should be installed in a dry, well-ventilated location. They should be protected from overloads and short circuits. They should be properly grounded to prevent electrical shock. Class 1, Class 2, and Class 3 remote control signaling and power-limited circuits are low-voltage circuits used for various control and signaling applications. The NEC specifies the requirements for these circuits, including their voltage limits, power limits, and wiring methods. It is important to note that this information is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer for specific applications and installations. Furthermore, always adhere to the latest edition of the NEC and any applicable local codes and regulations. When dealing with electrical systems, safety should always be the top priority. Take all necessary precautions to protect yourself and others from electrical hazards. If you are not comfortable working with electrical systems, consult a qualified professional. By following these guidelines and safety precautions, you can help ensure the safe and reliable operation of electrical systems. Remember, electricity can be dangerous, so always treat it with respect.